This is part 2 of lesson 7 of unit 8, volumes revolving around other axes. In this part of the lesson, we are now going to have a vertical axis of revolution. And so we are going to write the general forms of what these equations will look like. And we want to remember that we are taking our cross sections perpendicular to the axis. So again, we're going to start out by looking, what if we have one curve, and what is our outer radius and our inner radius, and then how would the function look? So for the first one, we have the curve here. We're now going to call this f of y because we're doing it, we're doing this with respect to a vertical axis. So we're going to go from A to B is along the y-axis now. So our capital R is going to go from the y-axis to the axis of revolution. It's going to be the longest distance, and so that distance is going to be C, because that's where our axis is, this horizontal distance here, which is C. Our smaller radius is going to go from the edge of the curve to our radius, our axis, and so that is going to be C minus our curve, which is f of y. So our volume will be pi times the integral from A to B on the y-axis now of C squared minus C minus f of y squared dy. And so when our axis is on the other side of the y-axis, and we have x equals c, and c is going to be a negative number, and we're rotating around our axis in this way, we're going to have our capital R be from the edge of the curve clear over to the axis. So we have this length of c here between the axis and the y axis, and then we have this length, which is measured by our curve f of c. So our capital R is going to be our f of, not f of c, f of y, I'm sorry. It's going to be our f of y plus c for that total distance. And then our shorter radius, our inner radius, is going to be this distance right here, which will just be c. And again, distance is positive. Even though c is a negative number, we're looking for that length, so that's a positive distance. So v is going to be pi times, and again, we're integrating from a to b, and a may not be 0. And we're going to see that going forward here, of our outer radius, which is f of y plus c squared, minus our inner radius squared, will just be c squared dy. Okay, now for the second two pictures, just like in the last video, we are going to be looking at two functions. So we have f of y and g of y. So again, when the axis is on the positive side, when x is a positive number, and we're rotating around the axis here, our bigger distance is going to be the distance from the curve farthest away from it. So that is going to be our capital R, and that's going to equal our total length minus this gap, which is caused by g of y. So here's where the gap is, right in there. And then our smaller radius is going to be from the curve that's closer to the axis, which stops at f of y. So little r is going to be c minus f of y. Okay, so our volume will look very similar to the other ones. So we're going to go from A to B, and you can see here that we aren't going from 0. A is not 0 in this picture, and it's going to be c minus g of y squared, for our radius squared, minus c minus f of y squared dy. And then finally, when our axis is on the other side and we're rotating around here, we now have switched positions. So the closest distance is always smaller r, and the longer distance is always capital R. So in this picture, our little r is going to be the distance c, even though c is negative, that distance is c, plus how far we are away from the curve here. So little r is going to be c plus g of y. And capital R is going to be the same thing. We have this distance c, and then we have this other distance here to the farther away curve f. So it's going to be c plus f of y. So now our volume is going to equal pi times the integral from a to b on the y-axis of f of y plus c squared, that's our capital R, minus g of y plus c squared, and this is dy. Okay, so our first problem that we're given is a calculator problem, so we can set it up and then solve it in the calculator. If you want to solve it by hand, it can be done. It's just a polynomial like we've been doing, but since we're allowed to use a calculator, why not? Okay, so we're supposed to find the volume approximation of the solid generated by revolving the region bounded by y equals the cube root of x, the x-axis, and the line x equals 1, and we're revolving it around the line x equals 2. So even though it's done in the calculator, it makes sense to draw you a picture because the calculator is not going to be able to give you the vertical lines. So here is my y-axis. There's my x-axis. And I have the cube root of x, which in the first quadrant is going to look like this, and it's bounded by the lines x equals 1, which will be like right here. And so I don't need this little part. I'll probably erase the whole thing, but x equals 1, so here's 1. And then we're revolving it around the line x equals 2. Okay, so here is our little region. And we are bounding it by this line here, so we need to know where that distance is there. So if we look at this point is the point 1, 1, so we're going out from there, so we're going to be integrating from 0 to 1. And so our two radii, so here's our inner radius right there, so that distance between 1 and 2 is 1. And our outer radius is going to be how far away we are here to the edge. So that is going to be 2 minus, and the first thing we need to do is solve our function for x because we're revolving it around a vertical axis. Okay, so we have 2 minus y cubed. So now our volume is going to be pi times the integral from 0 to 1 of our outer radius, which is 2 minus y cubed squared, minus our inner radius, which is 1 squared, dy. And you can put this in your calculator using x, and it'll give you the correct answer. So v is approximately equal to 6.732. And if you do want the exact answer, if you do figure it out, it comes out to be 15 pi over 7. Okay, next problem. This is one where we are not using our calculator. So we are supposed to use the equation y equals x squared, y equals 4, about the line x equals 3. So the nice thing is for this one, we do have a picture. Here is x equals 3. This is our line of revolution. We have the line y equals 4, which is going to be right along here. And then we have our function, which looks like that. It's going to hit the line y equals 4 at, if you want those points, at -2 and 2. We're going to be integrating from 0 to 4. And so now we have to find our two radii. So the long radius is going to be clear from this side of the curve over to the axis of revolution. There's our capital R. So first thing we should do is think about what this equation looks like if it's solved for x So it's going to be plus or minus the square root of y equals x. So you have a minus square root of y on this side and plus square root of y on this side. So this distance here in green is a square root of y distance, even though we have negative square root of y. And then, of course, we have this distance, which is 3. So our outer radius is going to be 3 plus the square root of y, or square root of y plus 3, however you want to write it. And the inside radius is going to be from this side of the curve to our axis of rotation. So there's our little r, and that's just going to be 3 minus the square root of x, because we just want this leftover bit right there. So our other inner radius is going to be 3 minus the square root of y. And for the method, it's going to be a washer, because we're going to have a hole there, since there's a gap between the axis of rotation and the figure itself. So our volume is going to be pi times the integral from 0 to 4 of 3 plus the square root of y squared minus 3 minus the square root of y squared dy. And we'll have to actually multiply this out and integrate it, since this is not a calculator problem. And so in our first parenthesis or brackets, we get 9 plus 6 square root of y plus y. And in the second one, we get 9 minus 6 square root of y plus y, and this is dy. So simplifying, we get the 9's will cancel, the y's will cancel, and we're left with, and I don't even need the parenthesis here now, just 12 times the square root of y dy. So this is going to be pi times 12 times 2/3 times y to the 3/2, evaluated between 0 and 4. So we get, simplifying, v equals, simplifying all this, we get 8 pi times 4 to the 3/2, which is 8. So we get 64 pi. Okay, next example, we now have a negative x for our axis of rotation. So this is at x equals -2. And we have the function 2 times the square root of x, which will look like this. And we also have the line y equals x, which is like that. So our region is just that shaded area in there. So our capital R is the farthest distance, so it's from the line to the -2. So we have a distance of 2, so let me put a capital R on there. We have 2, so this distance right here, plus that second part, which is just y, because y equals x. So it's the same whether it's already solved for x. So taking my other equation, and I'll square both sides. So x is going to equal y squared over 4. Okay, so my inner radius is going to come from this distance plus this little bit more right there. And so little r is going to be the 2 plus the y squared over 4, or 1/4 y. And again, we have a gap, so this is a washer. And so doing our integration, we're going to have that v equals pi, and we're integrating, oh, we need this point. Where do these two meet? And where does y squared, let's do it with x, it just makes a little more sense. 2 times the square root of x equal to x. So you square both sides, you get 4x equals x squared. So your zeros are at 0 and 4. So this point is at 4 here. You put 4 in the equation, and of course we have y equals x, so that's 4 on the y as well. Okay, so we're going from 0 to 4 of 2 plus y squared minus 2 plus y squared over 4 squared dy. So v is going to equal pi times the integral from 0 to 4 of 4 plus 4y plus y squared minus 4 plus y squared plus 1/16 y to the 4th. And this is dy. Simplifying, we get the volume equals the integral of pi times 0 to 4 of 4y minus 1/16 y to the 4th. Everything else cancels. The 4's and the y squareds cancel. So this is going to be pi times, and when we integrate, we get 2y squared minus 1 over 80y to the 5th, and we're integrating between 0 and 4. And now it's just substituting in, and we get, and I'm just going to skip to the result. You guys can check this. You should get 96 pi over 5. Okay, and then finally the last 3 examples are all calculator examples. So the key here is to set them up correctly. So the first one is x equals e to the y, x equals 1, and y equals 1, and the line y equals 1. Okay, so we have this line x equals 1 here. So dot in right now. Now this you want to solve to put in your calculator. You want to solve that for y. So x equals e to the y. So that means ln of x equals y. So that's our equation. So what we're going to find is that the way this graph works is it comes up through here. If you think about the natural log graph, it crosses the x-axis at 1. So our region is actually over here, right there, and we're rotating about this line y equals 1, and so we're right up against our axis of revolution. So we actually have a disk here. We're not going to have a gap, and so our outer radius is going to be just this distance right here, which is our 1, our y equals 1, minus our function, which is ln of x. Okay, and our inner radius is going to be 0 because we're up against the axis of revolution, so we don't have an inner radius. So this becomes a pretty simple integral to do in the calculator. Now the question is, though, what are the limits of integration? And so we're doing it from x equals 1 there. So what is going to be the upper value? So we want to know when y equals 1, so that's just going to be e. So we're going to integrate from 1 to e of 1 minus ln of x dx. And when you put that in your calculator, you get that your volume is approximately equal to 1.372. Okay, next one. We're doing it around a vertical axis now, and so here is our axis here. This is x equals 8, and we have the cube root of x, which is going to look something like this in the first quadrant, and the line y equals 0, so we have this chunk right here. And again, we don't have a second function, and we're right up against our axis of revolution. So our inner radius is going to be 0, so we have a disk again. And our outer radius is going to be just the distance from the curve to the line. So our r is going to be, it's 8 units away from 0, and we're going to subtract off our function, but first we will need to solve it for x. So y cubed is x, so this is going to be minus y cubed. So that's our outer radius. So now we just need to know what this point is here, because we're going from 0 to that point. So we just need to substitute 8 in our function for x, and we get right here, so y is going to be the cube root of 8, so y is 2. So our volume is going to be integrating pi times 0 to 2 of 8 minus y cubed squared dy. And when you put that in your calculator, you're going to get 258.508. That's supposed to be a decimal point. That's pretty messy looking. Let me rewrite that again. Okay, and then the last one. Now we have 2 times the square root of x, which we've seen before. So that's just going to be a little steeper version of our square root function. The line y equals 6, and we're revolving it around the line y equals 6. So again, we're going to be up against the line, so this is another disk. And so we're just going to see where our curve is going to hit that. So here is what we're revolving. And now we just have one r again. And our r is going to equal just that distance. So this distance here, since we're revolving it this way, we need to find where, if y equals 6, oops, it should be an x, squaring both sides. So this point here is at 9, so we're going between 0 and 9. So our outer radius is 9 minus the square root, or 2 times the square root of x. And we have no inner radius. And so our volume is going to be pi times the integral from 0 to 9 of 9 minus 2 times the square root of x squared dx. And this is going to be approximately equal to 169.646. And that's the end of our lesson.